This section is going to be about arithmetic sequences, so hopefully it's a review of things you've already seen in the past, but if not, we'll go back through the formulas. Also, we'll cover arithmetic series as well. So here's sort of a classic example. You're trying to figure out how many seats are in a section of an auditorium. It starts with 20 seats in the first row, 23 seats in the next row, 26 after that. And this pattern is going to continue for the rest of the section. And the question is, how many seats are in row 50? If you try to write this pattern out, it would be 20, 23, 26. We can infer next is 29. We really don't want to have to do that 50 times, so we want to come up with some kind of pattern and figure out what that last number is going to be, that 50th term, what that's going to be. So generally what most students are able to start recognizing is that we are counting by 3 each time. So we're adding 3. We'll come up with some terms for these things in a minute, and that'll lead to the formula. So we're adding 3 each time. And usually the way I see this go in class, if I ask, all right, well, how many times do we add 3? Well, this is kind of a little tricky, you have to be careful of. If this is the first row, and you're going to add 3 a bunch more times to make it to row 50, you're going to add 3 49 more times. So an easy way to get this would be 20 plus 3 times 49, which is 20 plus 147, so 167. To make a formula out of this, we really need to start coming up with some terminology. So the first term, as always, is a sub 1. This amount that you're adding by is going to be called D, and that's your common difference. Now normally this number of terms that you're looking at is n. You have n rows, 50 rows. And we just really want to come up with a way to get 49 from 50, which is just 1 less. And the reason it's 1 less is we've already counted the first row, so we need 49 additional rows. So let's start putting these things together in terms of a formula. So we have A1 first, plus the common difference, times the number of rows, but minus 1, so n minus 1. And that's your arithmetic sequence formula there. So here's the official start to A2. Now that you had that little preliminary thing to think about. So it is arithmetic sequences in series. This is something I'm going to come back to in just a moment for series. I think it's the best way to illustrate the formula. It's a nice visual. Let's go ahead and get this geometric sequence formula. Now, the way you'll know something's a sequence is because sequences are made of terms, and you're just looking at a term in the sequence. Series is the sum of all of the terms, so for series we'll see S sub n. So series has an S, sequence is just a term, so A. So let's go ahead and put the formula we came up with. That's going to be A1 plus D times n minus 1, which you saw the pieces kind of come together. I think that's probably the easiest way to illustrate it. It's just that example we did with the auditorium. Now for the sum, here's an easy way to do this. So check this out. We're starting off with a little pyramid shape. It's got 10 objects in it. Not too hard to see that. You can count them up pretty quick. What I'm going to do is a little strategy where I start moving rows in a particular way, in a pattern. And it should sort of lay this out for you in a really organized way that you can almost look at it and tell how many dots are there. So keep note, there's 4 rows right now. First row was 1, last row had 4 in it. So here's the little trick. I'm going to take the first row and bring it to the bottom. And I'm going to take the next row down and bring it to the next row up from the bottom. And I'm just going to kind of scoot these so it looks nicer. That's probably pretty easy to see visually. That's a rectangle and it's 2 times 5 or 10 dots in it. And if this was 100 rows, we could do the same strategy. And the idea is because it's increasing, if you start from the top and go down, it's increasing at the same rate as it's decreasing down here. So you just combine them together and the rows are the same length. You get half as many rows and each one is the same length once you add the beginning and the end. So let's approach the formula from an area perspective, since I mentioned a rectangle. If we were to draw a rectangle around it, well, how many rows do we have? Well, we start with 4, so we're going to have half of those now, n divided by 2. And to get the length of each row, we took the original first one plus the last one, and it turned out that all of them came out to be that exact same length. If you have an odd number of rows, this will still work. To do it visually, you'd have to cut one in half and be kind of weird looking, but it would still work. So the formula does hold. And I think that's an easy way to see the formula and how it comes to be. It's this side, or this height times this width, if you're thinking rectangle. So n divided by 2 times a1 plus an. So there it is written out formally, n divided by 2 times a1 plus a sub n. Now sometimes, and I'm going to show you an example here towards the end, sometimes you don't quite have enough information to do this. This is the easy formula. There's a more lengthy formula that you can use too, and I'm going to show you that one. So again, I'll show you one in a little bit where you don't quite know the last term. So there's two ways to go about it. You can examine the sequence and find the last term and then plug it in. Or there's a longer formula you can use for series, and you can just be done right away. So what we want to do to get the other formula is we know that a sub n, the sequence formula, is a1 plus d times n minus 1. So if you plug that in for an, that gets you to here. And you can just combine what you can. So n over 2 stays there. a1 plus a1 again is 2a1 plus d times n minus 1. And I usually put square brackets to make it look a little neater. But that's the alternate formula. That's another way to get the series. Again, if you don't, and you'll kind of know, if you're missing enough information, you can't quite do this formula, you'll pretty much know that this is probably going to be something to try. And it's possible that doesn't work either, but usually this is the one that's going to work. Sometimes you just have to play around, do a combination of finding terms in series so you can plug those in. You'll get the feel for that as you go through some examples. The last thing to talk about, which is really not much of an issue for arithmetic series, is what happens if we have an infinite sum. So if I go back to that pyramid idea, well, if that went on forever, think about what the total number of objects would be. If these rows, if there's an infinite number of those rows, and each time they get bigger and bigger and bigger, it's just infinity. There's an infinite number of objects. So this is really kind of a silly result, but I think it's worth talking about because it's going to lead to an important calculus idea called convergence. When we get to geometric series, you'll see how that plays out. So I think it's kind of important that as you're trying to get things to converge with geometric series, that you think about how arithmetic can never do that. There's an infinite arithmetic series. It just has no total. The total's infinity. There's no definite answer. All right, so the first example is find an equation for a sub n. And here we're given some terms in that sequence. I will tell you that some of the examples I'm going to cover here hit the highlights of what's in the homework. You might not necessarily see the arithmetic sequence or series formula pop up, but they are related to arithmetic sequences and series, and the same skills are going to pop up. So just kind of keep that in mind. Those formulas might not apply to every single problem you do, and this one they're not necessarily going to apply here either. So let's kind of look at what we got. Well, the big hint I would focus on, these two are fractions, so let's see if we can make these other terms fractions. Now, if I wanted that to be over top of 3, that would have to be 6 over 3. And if I wanted this to be over top of 3, it would have to be 36. Because that would be 12 over 1, multiply both by 3. This would be 2 over 1, multiply both by 3. And hopefully the pattern's pretty obvious now. On the top, it's 6, 16, 26, 36. There's a common difference going on, and that's how it relates to arithmetic sequence. The bottom's staying the same. It's always 3, but the top starts at 6, and you add 10 each time. So to come up with a formula, we'll start with a fraction, because I know it's a fraction. Start with the easy part. 3 is on the bottom every time, no exceptions. For the top, now I'm going to kind of start with what I think is an easy way to see what's going on, but then we got to really check our work and make sure it's checking out. So I'm going to start with this idea. It's 6 plus 10n. Now that's not going to work, and I need to check and show you why. But it's a good place to start, because you start at 6, we add 10 every time. So 10 times whatever number you're on, number 1, number 2, number 3. Problem is, if I plug in 1 here, this is 10 times 1, so this is 16. So if I plug in 1 here, which should be the first term, it leads to the second term. So the easiest fix for that is to make that 10 times n minus 1. So So that's going to be 6 plus 10n minus 10 over 3. This is going to be 10n minus 4 over 3. And let's check and make sure that's working out. So if we put in 1 here, this is 10 minus 4, which is 6, over 3, which is 2. That checks out. Put in 2 here, that'd be 20 minus 4, so 16 over 3. So it seems to be working. Just always make sure you reduce. I started here with some distributive property that could be done, so always reduce it as far as you possibly can, and then you should be good. All right, on this one, we're going to take a recursive sequence, and then we're going to see that it's arithmetic, and we're going to turn it into an arithmetic sequence. The reason that's helpful, remember recursive, if I want to get, say, the 50th term, then I've got to go through and find all 50 terms to get there. If it's an arithmetic sequence and I want the 50th term, then I just plug in 50 for n and I'm done. And that's it. I don't need to find all the other ones. Just find that one. So let's see if we can figure out a pattern that's going on, turn it into arithmetic, and then redefine it so it's really easy to find terms that are way out in the sequence. All right, so A1 is 4. Let me just kind of make a list here. A1's 4. So A2, you would take 4 and plug it in here. So 4 plus 3 is 7. To get A3, third term, plug in 7, add 3, and that's 10. And some of you are probably going to spot this pretty quick and just see that, oh, the common difference is 3. I'm just adding 3 every time. And that's what's happening here. So let's try to define this. So A sub n, start with 4, and add 3 each time. But instead of just 3 times n, because if I put in 1, let's do that and just kind of see how it plays out. I just did n, put in 1, I would get 7, which is the second term. So pretty common thing that's going to happen. First term plus common difference times n minus 1. But think about that, that was verbatim the definition of arithmetic sequence. So we can think about it that way and just use the formula if that helps. So either way, whatever works, but always reduce this. So 4 plus 3n minus 3. So 1 plus 3n. And that'll do it. That'll define this as a arithmetic sequence instead of a recursive sequence. Example 3 says find the partial sum. So this is hopefully not a new term, but just in case. Partial sum means you're adding up a set number of terms in the sequence. So if n's 11, I'm adding up 11 terms in the sequence. Partial sum is important because eventually we're going to look at those infinite series that go on forever. Now again, with arithmetic, that's kind of pointless because they would just add to infinity or negative infinity. There's no point in doing that. So for arithmetic, it's always going to be a partial sum. There's always a set number of terms you're going to add together. So let's see what we can figure out here. We've got A1 is 2. Each time we're adding 4, so common difference is 4. We know we've got 11 terms. So what I could do right now is use the sequence formula to figure out that 11th term. And then from there, I could do the series formula and finish it up. I'm going to use that second series formula and just get it all done at one time. And that was n over 2 times 2a1 plus d times n minus 1. Which is all it's doing is combining the sequence formula with the series formula, put them together, and you get to come up with this other formula that's going to work. But the issue is I don't have, if I did the first series formula, I don't have a sub n. I have to find that first, so that's why this is helpful. But this should be enough. So 11 over 2 times 2 times the first term 2, plus the common difference of 4, times n minus 1, so 11 minus 1 is 10. 11 halves times 4 plus 40. So 11 halves times 44. I'm going to reduce that. You've got 44 on top, 2 on the bottom, so 22 over 1. And 11 times 22 would be 242.